Yeah, so I got to figure out how to like make Canvas publicly available, I guess. I need to figure that out. I did figure out how to publish it, right? Because now I see you guys are all, yeah, so baby steps for me here. So I'll have to figure that out, but I'll try to. Yeah, so that like stuff is made available. I see that we have a camera, so thanks whoever figured that out. Yeah.
I did a plus last time. You were just gonna say that you were gonna share your email to contact you.
Oh, right. And a lot of people have been figuring this out. So, I was a math student here, and then a postdoc, and a long time ago. So I had a math account. And it turns out when I came back to the math department, it still existed. It had long ago been put into a pretty bad state, so it wasn't functional. But the guys over there made it available, and so I'm back to where I was a long time ago. So, anyways, my math email account is probably the best way to contact me about this class, and that's earnshaw@math.utah.edu. So my last name @math.utah.edu. Okay. Other questions? Thanks for bringing that up, Brent. That's a great reminder. Okay. All right. Well, we can get started. This is a better room, right?
Yes.
Yeah. First of all, the Warnock building is like decades ahead of the Merrill building, right? Like in terms of everything. Like there was an HDMI cable over here, so that was nice. We're using interfaces from like the nearish past. Okay, so I'm gonna try. I don't know how many lights I should turn on. I'm not sure to turn off that. Oh, that one. So I should probably put on some lights, right? How's that? Is that pretty good?
That's good.
All right. Okay, so we just kind of barely got started with like all the cool examples. That was all the cool examples of deep learning there aren't anymore. There's actually so many, and it's like incredible. So I don't know if I know a lot of you are like graduate students. Some of you have told me that you're actually using deep learning in your research, and you probably know lots more about certain networks and architectures than I know. It's a big topic, and when you get on archive, like I don't know if it's every day. I can't really track it that way, but like every week there's like papers on there that, at least by the titles, they're like kind of mind blowing. And then when you look at them, you can sometimes they really still remain mind blowing. Other times it's just sort of like an overblown claim, but it's really incredible what's going on. There's just so much going on here. Being enabled by neural networks. And it's so funny because when I was a student, like an undergraduate student many eons ago, like neural networks were like laughable. They were like people, like if you would never use the word neural network, you definitely didn't use the word artificial intelligence, because people will just be like, the 80s are gone, you had your chance, it didn't work, and a couple of people said, no, we can still make these things work, and they really kept working at it. And I mean, it was kind of a convergence of a lot of things, new ways of training deep networks. That was one of the big ones. And we don't use these ways anymore, but there were things called like Boltzmann machines, restricted Boltzmann machines in particular, that were used. But really what happened was GPUs. Someone figured out like, hey, we can do matrix multiplication really fast on a GPU. And then we went from like the Stone Ages to like the modern age really fast. Like in less than 5 years, it was like totally different. And it's really because of GPUs. So like, if we all had bought NVIDIA stock a year and a half ago, it's worth 10 times what it was a year and a half ago. Mainly because NVIDIA like totally owns the data center GPU market. And in fact, they actually, so who's like really like into hardware and stuff and knows like the NVIDIA story around their GPUs? Anybody? Okay, well, so this is not totally accurate because I don't know all the history, but they were for gaming, right? The GPUs are, the G is graphical, and like it's not graphical like a math graph necessarily. It's like graphics, and people started realizing that you could like do these things really fast, and so for a long time people were just using these like consumer grade GPUs. In fact, people still use them. In fact, like at Recursion, we have a ton of consumer grade GPUs actually, because you can put them all together. It's kind of like, you know, in the old days of, it's not even that old, but like Hadoop, you know, is like, oh, you just get a bunch of crummy disks and computers and you can all hook them all up and then you know, you get this massive storage system and it's performant and all that. Well, kind of the same thing happened with GPUs. Well, you know, recently, so I guess, I can't remember exactly when the Voltas were released, but the Volta really represents like the first serious divergence from like the gaming architecture to like something specific for deep learning. And they released it, you know, it cost a fortune, but they're really cool and they're really fast and they have a lot of memory and blah, 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 blah. And then, like, I think it was about 6 months ago, they came out with this thing and that said, like, data centers cannot use their consumer grade GPUs anymore. It was like, it's part of the license agreement for these GPUs. So all of a sudden, so they basically cornered the market, and then they said you can't use our crappy ones in data centers. You have to use our really expensive ones. And so right now, so there's like two major appliances that NVIDIA sells called the DGX1 and DGX2. Both of them have 8 GPUs in them. They're both Voltas. These are V100s, and I can't remember if, I think the DGX2 has like a 32 gig one, the memory. But when the DGX1 came out, it was $135,000 for these 8 GPUs plus like a bunch of flash storage. And then the DGX2 is basically the same thing, but it's also but now it's got these better ones. And it's like, I can't remember the asking price, but it's like $300,000, something like that, for 8 GPUs. So yeah, and people are buying them. Facebook bought 256 DGX1s, like when they came out, and then they just hooked them all up, and then let Russia in. I don't know if that actually was good, but it's amazing. NVIDIA in particular has really changed, and it's weird to me that like no other like hardware manufacturer has figured out how to like take any of the space. Like nobody, like it's now laughable if you were like training on anything other than NVIDIA. And really, the way that they did it is there is a language for working on the GPU called CUDA. I actually don't know what it stands for. Anybody know what CUDA stands for?
Compute Unified.
What?
It's something with Compute Unified.
Doesn't matter, but it's basically a language for working on a GPU. And everything, all of the frameworks, everything to do with deep learning, wrote CUDA code and wrote APIs for the masses to consume it. And so no one else can put CUDA on their GPUs, and therefore everything only works on NVIDIA hardware. So that is how you corner the market. That's how you get your stock to go up tenfold in a year and a half. That's all you have to do. You have to be in business for like 30 years, struggling to get like the few nerds that like really loved gaming, and then to buy a couple of GPUs, and then find a whole new market to take over. So, anyways, I'm not sure why I went off of that, but that's kind of an interesting aside. Okay, so let's get going here. So we're in this week of like there's machine learning basics, and I really do mean basics. I really am not going through like the whole of a machine learning course in 1 week, but I'm touching on aspects that we will continue to talk about throughout the semester. So like, what is machine learning? So they're like the first like real machine learning textbook was written by a guy named Tom Mitchell, and there's this like definition in there. And this is like, this is like the definition that if you write it down on your qualifying exam for your machine learning PhD, I guess you get it right because you'd say Tom Mitchell said it. But it says the computer program is said to learn from experience, E, with respect to some class of task T, and performance measure P, if its performance at tasks in T, as measured by P, improves with experience E. So it's just like all it's saying is like, if it works on these tasks, if you have this algorithm that kind of works on these tasks and is getting better at it as measured by some way of getting better, then you can say it's learning. Well, that's not really helpful, actually. Like, that doesn't really, I mean, it's just super intuitive, right? So, if you put a couple of like set symbols, then maybe it feels like, you know. But it's, it's actually not that helpful. So, this is actually the way I think about machine learning, and a lot of people think of it this way too, but I think it's just really pretty helpful. So, there's like structure in the world, and our job is to learn what that structure is. Yeah, there are tasks that there are data sets that sort of like are examples of the world. There are tasks that allow us to learn on them, and we measure our performance. But really what we're trying to do is we're trying to learn some sort of structure in the world. And here's an example of what I mean. So here's somebody's face. I'm not sure who that is. No, I'm just kidding. This, like, you look at it, like kind of like we were talking about last time. Like nobody like looked at that and was like, oh my gosh, something's wrong there, because this is like the structure of a face that we expect, right? So, maybe the world we're talking about again is faces, but there's just some sort of structure there, and we are learning machines. We have experience in tasks and ways of measuring, and we just know that that's like really normal. Now, all I'm going to do in the next image is just rearrange some pixels. So all the pixel values are the same, but you probably have a pretty strong reaction to it. Wow, yeah, that does not seem right, does it? I mean, all that's happened here is the eyes are turned upside down and the mouth is turned upside down, right? So all the pixel values, like as a group, all the values are the same. It's just I sort of rearranged where some of those values are. So something's wrong there, right? And you noticed it right away, and I did too. And it's like, that is not part of the structure of this world. Even though like the pixel value, like as a group, as the distribution of pixels would be the same, like there's something about the way that they're structured there, that there's something that's wrong. And like in machine learning, we're basically trying to say like, figure out that like the thing on the left is good structure, the thing on the right or in the middle is bad structure. I think this is sort of interesting. This is just more like visual stuff. So here it's actually this same image just turned upside down. Or maybe just flipped across the axis. You actually had less of a bad reaction to that, right? Isn't that weird? Yeah, we are like the ultimate learners, I think. Probably still, for a while, maybe a couple of years, hopefully. Even we're like tricked by this stuff, right? Like this is, like you'd almost, like if I probably could set up some sort of like behavioral experiment and like really quick look at it, say like this is right or wrong, and you'd probably go right, wrong, right. Anyways, even we get tricked. So what do we mean by learn the structure of the world? Well, a really good way of doing this is to assign probabilities to these structures or these configurations in the world, and to say whether something is likely to happen or not likely to happen. It's actually a really awesome framework, and surprisingly, most of machine learning can be constructed in this framework. So we want to say something like the probability of this particular configuration of things is likely. It's a lot bigger than 0. I mean, I don't know, maybe we say it's 1 or something like that, but this is a very likely thing to see in this world. Where the next one, we want to say it's basically 0, right? It's like we want the probability of that thing to be 0. That is not a structure that is observable in the natural world, anyways. On your computer, you can make a lot of things happen that aren't real, but anyways. And then, even though we were tricked by it a little bit, just because this is just like a rigid rotation or transformation of these pixels here, the whole thing. Even though it kind of seemed right to us, that still should be assigned 0, right? Like there's something about these certain transformations that should preserve the probabilities here. So Adele will take us into the deep learning here. So let's kind of formalize this a little bit more. So there's this funny looking X. This is going to be the set of all possible configurations of the world. Now, in machine learning, the world changes all the time. Like, we're not trying to learn like the whole world. Like, we pick really simple domains, actually. This is where most people will like talk about artificial general intelligence as like not even being a possibility even close, because even though we've seen lots of amazing progress, it's like in very, very limited domains. Like, so we were able to, you know, I showed you those images where we generated those awesome faces of celebrities. It's like the world there was like celebrity faces, but it was like the world was more like crops of celebrity faces looking forward, you know, like all kinds of constraints on whatever this world was. But within that world, we're trying to learn some structure. So we think about like all the possible configurations. So like within that world of like the celebrity faces, we we can think about like all the ways that all the values of the pixels you could have like in an RGB image. Even though I have grayscale. And then the structure of the world is described by a probability distribution on that set of configurations, right? It's assigning to some 0, like that could never happen. It's assigning to something very large, saying like this is very likely to happen. And this is a great way to encode what structures are likely in this world. So when we apply it to some sample X, we're saying this is the probability of observing this configuration X. We can also state this in a little bit different way. This would be something like the probability of observing features Y given a configuration X. So it might be that we're not interested necessarily in the configuration itself, but some features about it. Like, I don't know, maybe like color of the eyes, or I don't know, color of hair, or I don't know, whatever kind of feature you might think of. You might be actually interested in not just assigning a probability to that structure being likely, but given that structure, how likely are some features about it. When we're thinking of like this first thing right here, this is something that's called unsupervised learning. So we're basically just learning the structure of the space that we're in, like what's likely and what's not. If there's an unsupervised learning, then there must be a supervised one, and that's the other case, where we're trying to, like, in some sense, pair up something about the configuration and to learn that, trying to predict that. So the probabilities are allowing us to do that. And so what I've written here, by the way, is, I had this thing up here where, I said it was the probability over all possible configurations. But, the thing is, when we're doing real machine learning, we never have access to all the configurations in the world. We never have access to the whole world. I mean, unless like the world is like really simple. I don't know. There are definitely situations, but then those don't need machine learning. So what we do instead is we try to approximate this real distribution over the real world by some model. And whenever you see this sort of like, semicolon and the theta, you're in model world. The theta are like the parameters or networks, we call them weights, of this model. It's sort of like the things that we can tweak to change what this probability model is saying about X. Some parameterization of the model that allows us to change what its output is. And same thing for the supervised case. It's just we're instead saying something about features rather than about the structure itself. Okay. Thanks, Adele. That was nice. Questions? This is like the whole of supervised and unsupervised learning in one slide. That's all there is to it. I mean, at a very abstract level, this is what we're doing. Okay, so let's go back to some of the examples we looked at last time. So here's our celebrity faces. So what we're really doing here is we're sampling. So it's like we have learned an approximation anyways. Well, no, actually, sorry, this is actually a data set. So we've learned a model on this data set. And what we're doing here is we're basically sampling from it. We've learned this probability distribution. It's telling us what's likely, and we're sampling like the likely configurations from it. And that's why this is so amazing, because there are so many like configurations in between these that are like, that don't look like faces at all. But when I sample from this thing, I actually get things that look really good and sharp. So that's pretty awesome. We have lots of examples here, so let's keep going through. Harry Potter's is sort of something similar. Our data set's Harry Potter. We train on all of Harry Potter, and we just sample. Now, this is not exactly how it works. Like, you don't just sample that whole chapter from the Harry Potter distribution. That would be awesome, but that's not really how it works. So how it really works actually is that you have this whole, whatever, some substring, and then you like sample the next character, and then that character goes on to the string, and then you use that now string as a seed, and you sample the next one. But anyways, you can sort of think of it as I sample the whole chapter from this probability distribution I learned. Here's something that we haven't talked about. This is a really awesome combination of images and text. This was done by Andre Karpathy and Fei-Fei Li a couple of years ago, where they took this data set called Coco. And Coco is this, it's a Microsoft data set. It's, I believe, from Bing. So you might have heard of this thing called Bing, sort of like Google. Search. Anyways, basically, like they were able to take like people had actually annotated some images somehow using Bing. I can't remember exactly how it was done, but the point is that there were images, and there were like a bunch of text that should be something about. And there were actually like multiple. For a lot of the images, there was like actually multiple annotations for the image. And so, just describing what's in there, right? So it's like, man in a black shirt is playing guitar. So what's cool is that this is actually samples of stuff that wasn't trained on. So like, they took the Coco data set, they broke it up into a training set and a test set. They trained on only the training set, and then they test out what they're doing on the test set. And they actually have a rigorous way of defining how well they did, not just by like us reading it and saying that was good, but here we're using like the eyeball metric to say, yeah, man in black shirt is playing guitar. That's pretty much what that is. Not quite right. It looks like he's maybe tuning the guitar, but anyways, like pretty amazing. Just from the image, you can actually output that string of characters that actually is describing that. And for most of these, it's like pretty good, right? Like black and white dog jumps over bar. Like that is what that is. And the fact that it dealt with black and white is pretty cool. This is actually really amazing. Like it learned what this is called semantic. What's it called? Semantic annotations. I can't remember exactly what it's called. But basically, it's like it's learned like what's in the image, and it's able to tell it to you in that string. Now, lest you think that it did everything really well, there's definitely things where it didn't do well, though it's not too bad, right? So, like, this is not so bad. Young boy is holding a baseball bat. Like, there's at least two things wrong with this, right? This is not a young boy. This is a baby. Babies don't hold baseball bats usually, so like this is something that didn't learn from the data set, right? And also, that's clearly a toothbrush. Stupid thing. See, we're still champions in the learning space. Still. A cat is sitting on a couch with a remote control. Well, it got the remote control, but how dumb is that? That's like a rodent of some kind. Actually, that's still pretty amazing. This one actually is pretty funny. A woman holding a teddy bear in front of the mirror. Yeah, it's like, I don't know, like if I look at this kind of differently, like that kind of looks like Winnie the Pooh's head. I don't know, teddy bear. Or maybe this guy looks like a teddy bear. It's funny, the mirror part is really funny to me. I mean, maybe the mirror was like this thing right here, maybe the glass. But actually, it kind of has like a mirror-like quality to it. But maybe that's just me like imposing it on there after I read the mirror, I don't know. The last one's really cool. I like this one a lot. A horse is standing in the middle of a road. Now clearly there is no horse. There's a road. There's clearly no horse there. But notice this like structure that's protecting what looks like maybe a fire hydrant. And then there's like this unfortunate like main-like thing right here. And that looks like 4 legs and the main, right? So like, I mean, think about this in terms of probability distributions. Like it's trying to learn the structure of the world that you gave it to learn. And this is pretty dang close. Now, if you had like 10 times the amount of data and there were more examples of horses actually standing in roads, it could learn to differentiate that from just standing outside, I don't know, the Alamo or something. I don't know what that is. But, you know, maybe it could learn to do that, but like, it's only as good as like the stuff it's learning on, right? And this really is examples not of like complete failure, really of just like incomplete observations of the world. Pretty cool stuff. Oh, right, sorry. This was just to say that, remember, we're really not sampling from like the actual world distribution, it's some model of it, right? Because that's all we can do is train that. Okay, so, oh, this is something else they did that's really awesome. I guess I should probably put that out there too. So they took Coco and they drew these bounding boxes around the stuff that's in the image so it could train on that as well. So not only was it producing like a description of the image, it was also saying, you know, dog, well there's the dog. So not, you know, it's not only saying that like there's a dog in there, but it's actually telling you where the dog is in the image. And you know, where the fence is in the image and where the ball is in the image and things like that. So it's like it's even showing deeper understanding of what's going on in the image. And there are like a few like famous images that keep being used over and over in like machine learning examples and papers and stuff like that. And this happens to be one of them. So I don't know. You'll see it all over the place. So I put Coco Plus in there because they actually did these hand annotations out of the bounding boxes so it could learn to associate, to learn to take the words it was producing and to say where the bounding or where the object was in the image. Okay, so there's this is self-driving cars. There's actually an open data set now. It's called BDD100K. This is a total abuse of notation because it's actually not. We'll get there at the very end of the semester, but like this is pretty abusive. But just go with it right now. It's like at time t you're this, so what do we do at time t plus 1? But there's like awesome data sets out there that are actually images. There's no LiDAR data in this data set. It's all cameras. But it's like totally annotated, right? So like all the videos, it's like each video is like 40 seconds long, and you'll have like all these different kinds of annotations on it. So like the one up above is outlining where all of the lines in the road are. So it's learning. So you take this training data, you know, this like for whatever these configurations are X, it's telling you like, let's learn the features of these. And really that's why this abusive notation is like really what you want to do in self-driving is like, what do I do next? Not necessarily like predict the features of the next frame, but anyways, what do I want to do next? But what's cool is like these data sets exist. Like you could go download BDD100K right now and start your own self-driving car company. Probably won't go far, that's the bad pun, but you could. And someone went through all this trouble to annotate all this stuff. So like that's, you know, annotating where all the lines in the road are. This is basically like a segmentation of everything. So it's segmenting out different cars, plants, buildings, the road. Some of these have like different lanes or different colors and things like that. So like you can see everything. So you can learn to like avoid stuff, for instance, or learn to stay within your lines, or learn to like not crash, things like that. That would be important for self-driving. I think this is really interesting. There's all this learning going on, right? We're trying to learn about the world. But these data sets are limited, and they're limited like in really important ways, and self-driving cars contain a lot of limitations. So This is the moral machine at Media Lab at MIT. This is like, you can go get on it at moralmachine.mit.edu. You can get on right now and go take this test. And what this is, it's asking people, what should the self-driving car do? It's partly tongue-in-cheek because it's like, there's like stuff like this, like it's an empty car. You know, there's a bunch of old people with like one young person, I guess. And I can make the choice, like, it looks like there's only two choices. Like, either I can't go this way, I can't like crash into this thing, I guess, because I'm too close. So I can either like crash into the people here, or I can crash into the people here. So like, which one of these do you choose? Like, is there a data set in the world that you could like teach a car on? Where does our moral judgment come from? Like, don't answer this out loud, but like, what would you do in this situation? You kill young people.
Because you take a long distance. Like.
Takes longer distance, so maybe it won't be as killed.
Yeah, maybe nobody will be hit.
Yeah, maybe so. I think the point here is that like one group's going to die or the other. But you're right. You might have recognized this early enough to actually stop, and then nothing's problems. If you go and take this test, it gets progressively worse, and like by the end you feel like there's no hope in the world. So like, what do you do here? Like, how do you even frame this as a machine learning problem? I'm not sure. What about this one? There's people in the car. So do you choose to swerve into the barrier and kill the people in the car? Or do you choose just to keep going straight and kill the people crossing the road? And there's like a fat guy, like an exercising guy. And this is what they do. Like, they're trying to, like, when you take this test, they're trying to see, like, do you care more about, like, fit people or fat people? I mean, it really is like this. Do you care more about young people? You know, it's crazy, actually. And it's like, they're making a point, right? Which is, well, they are creating a training set. I don't know if it's a good training set, but they are creating a training set to say, like, what do we do in situations like this? But they're also like saying, intelligence is way more than learning the structure of the world. Unless you can pose like moral judgment as structure in the world. Maybe you can. I'm not saying you can't, but yeah, like there's like tough stuff that you butt up against when you start thinking about what does it mean to be intelligent. Yeah. What do you do in this situation? I don't know. Go take a test today. I promise you, you'll feel terrible at the end. Sure. Did someone just take it? I heard a moan, like, I just took it. The world is dark. So how is any of this possible? Well, like we talked about at the beginning, neural networks have made this possible. Now, there are so many different ways of like creating neural networks now that this seems almost comical, but but they all kind of have the same principles. So neural networks are like this. They have, well, I should say, first of all, this is something like the model that we are going to learn of the actual data distribution. Somehow, within all that craziness, we're going to somehow learn to approximate the actual observable world. Remember we kind of referred to theta earlier. So in a network, there's like two kinds of things. There are these nodes that are represented by circles, and then there are these edges in this graph. And the edges have a weight to them. This is a weighted graph. And they're called the weights. And literally there is for every, yeah, depending on the architecture, but literally you really have all these connections between all the nodes, and you're assigning some weight to them. And that's what a neural network is. Well, it's a lot more than that actually. But like it's pretty simple. So you're given some sample of data. It could just be X, like just like the configuration of the world, or you could also have these additional features along with it, Y. And you feed in the configuration. So this is like some sort of simple world. There's like 8 features in this world, X1 through X8. And yeah, and then what happens? Well, what happens is, we're going to talk about this in just a second, but there's a linear transformation that happens going from this vector to this vector. And it's basically just a matrix multiplication, possibly adding a bias term, just another, like a constant vector to it. And the important part for modern neural networks is here, there's actually a nonlinearity that occurs at each of the, after you do that, we'll talk more about that in a second, but the point is that you get some sort of output. From these 8 then give you these 6 in this next layer. Now this was your input, your observation. This is our first hidden layer. And everything in between the input and eventually the output is called hidden. So this is our first hidden layer. And it's actually just another, just like this was a set of numbers. I didn't actually say it explicitly, but this is a set of 8 numbers that represents this configuration of the world. Now, in this next layer, there's now, in this case, 6 numbers. And just like we did from input to hidden layer 1, we can go from hidden layer 1 to hidden layer 2. And we get another set of, in this case, 6. And then we finally output to our values at the end, in the last output layer. And we get y. Actually, it's a y hat. The hat always in machine learning means like the prediction that we're making. It's just like a standard notation. You'll see it everywhere. So remember, there was this actual y possibly, if we're doing supervised learning, that's associated with this configuration x. And here what we're doing is we're outputting something that, in this case, we're calling y hat. And this is our P model. The true output is y. And this model is good if, the output is like, if our predicted output is actually like the true output. Like, good can mean a lot of different things, and this is all the details of how you get all the different kinds of learning that happen. But this is like basically what it is. So we're trying to learn these probability distributions. So there's a couple different kinds of problems in machine learning. They basically like kinds of or types of tasks. There's basically 2 types of tasks, and they're not just 2, but like these are the 2 main types of tasks that we might care about. One is classification. Classification means you have some sort of finite set of labels that you're trying to assign to the configuration X. And literally when we're doing neural networks, we actually usually want the output layer to actually be a probability distribution. We're actually saying this is a probability distribution. We actually, there's a very typical last transformation or last activation for this last layer called softmax, which basically is taking a bunch of numbers and turning it into a probability distribution. It's a pretty simple transformation. But anyways, you actually literally get a probability distribution. And it might look something like this. Our predicted y1, probability of that being the case, like class 1 is 0.1, and for class 2 it's 0.2, and for class 3 it's 0.7, for class 4 it's 0.0. So I don't know, I just made up some numbers that look really nice and added a 1. So this is literally a probability distribution. And you can use that for a variety of different things, but usually what you do is you say, okay, well, whatever is the most likely thing there, the thing with the highest probability, is you say that's the class. When I'm doing classification here, I get these probabilities out. We think that this is an example of class 3 because it's been assigned the highest probability. So you say, so the classification task actually takes it one step further and says, I output a label of class 3. But it's used this network to determine what those probabilities are. The other type of problem that we have is regression. And this is like basically getting like any kind of output you want. It's all real numbers. In the end, like these y's could be any real numbers. We don't have any restriction like we want this to be a probability distribution, but we still want to use the idea of like this telling us something about the likelihood of this configuration existing in the world, or of these features being true of this configuration in the world. And a real common way to do this is something like the following. you actually pick some sort of parametric form for that distribution. In this case, it's just some normal distribution. And you say that the output from this model, this y hat, we're predicting the mean of it. We're predicting the mean of this distribution. And here I don't have the covariance matrix being predicted, but you could also predict that. There's no reason why not. But you know, what we're saying is, okay, what the prediction is the mean, and now we're asking, what is the likelihood of the actual, the true output under this model? Did we get a mean that makes this likely? And this is a really nice way of taking a regression problem and putting it into one of these, like a probability framework, so that we can think of these problems all under some unified framework. And why that's important is because then you can do things like maximum likelihood estimation of the weights. Now remember, what we're trying to do is we're trying to find weights that make this a really good estimator, going from input to output. Weights, again, being what the values of the edges are here. We're trying to learn those weights theta that make this really good. And one of the main tools for doing that is called maximum likelihood estimation. What that means is we're asking we're asking for the weights theta that maximize the likelihood of our data. And we're going to spend more time on this later. I'm not going to go into it deeply now, but we'll see this. We're going to see this a whole bunch. The word likelihood here is coming directly from Bayes' rule, which, if you learn anything in probability at all, if you learn one thing better than this, this is like the thing that drives everything in probability for some reason. So there's this nice formula for saying, if I have, this is called the prior, if I have some sort of prior distribution, some sort of like prior knowledge about what the weights in this case should be, and I couple that with the likelihood of the data under those weights, this term is called the likelihood, then that's proportional to, meaning like it's equal to that up to, with some constant factor. That's equal to the posterior distribution, which is the probability of the weights given the data. And this is like a super useful framework. In fact, it really is the case for basically like everything we're going to look at in this class. All of our networks are going to be trained from within this framework. Now, we do something called gradient descent. We're going to talk about that, I guess it's next week. And an approximation of that called stochastic gradient descent. So it really doesn't feel like we're doing argmax here. But in reality, this is what we're doing. We're using this as a framework and coming up with schemes to maximize this for our networks. This is a really key thing to understand about machine learning and about how we think about solving the kinds of problems we're trying to solve. And what's nice about this is this whole framework works for like no matter what the particulars of the network are, whether you have a classification problem, a regression problem, whether you have an unsupervised problem or a supervised one, you can basically put this all in this framework and you can think about these problems. In fact, most people, so like Mr. Joshua Bengio will always try to, when he's working on new problems, he's trying to put it into a maximum likelihood estimation framework so that we can use all the tools from there. So anyways, this is a really key idea. Okay, so we're about to move on to something a little bit different. So let's come back to this and let's see, just stop there. So questions? I've been talking a lot and I wish I would have brought a water bottle. I did last time, I didn't this time. Questions? All of you are like machine learning experts, so it's like super boring, right? Or all of you are like not machine learning experts and this is like mumbo jumbo. We're either one or the other. Or we're just like passive and who cares?
What's that sigma sign?
So this is a normal. This is a normal distribution. So a normal distribution is parameterized by its mean and by its covariance matrix. So like in a one-dimensional case, you'd have you have like some number here to be the mean and some number here to be your variance. When it's multidimensional, then you have to take into account not just the variances of all of the features, but the covariances amongst the features. So, anyways, just the point is that a normal distribution is parameterized that way. And what we were doing in this regression problem is learning the mean. We were learning some estimator of the mean given a configuration of the world. Yeah.
So I've learned Bayes' rule before, and I see what you're saying about the maximum likelihood estimation, but maybe this is a topic for later that we're getting into, but I guess I just don't see how we relate them. I'm not understanding the relation there.
Between this and this?
Yeah.
Oh, all I was actually saying about that is that we're calling this likelihood because we're maximizing a term that looks like this, and this looks like the likelihood term in Bayes' rule. And we will use this a ton too, actually. The prior term is how we regularize networks in the sort of Bayesian maximum likelihood estimation framework. It represents prior knowledge about what we expect of the weights, and we encode it in a distribution like that.
So does this formulation for regression work with a distribution as normal?
Yep, totally. Any distribution. So like if you think that your output is parameterized by something else. I mean, notice we had a categorical distribution up here. Like this is like, it's essentially the same thing. It doesn't look very similar because we move between discrete and continuous spaces, but it's essentially the same thing. You can use any distribution as long as it's parameterized, right? What all a network is doing is estimating the parameters of your network. Estimating the parameters of your distribution.
So why are we associating a probability distribution to our outputs? Like giving our y1, y2, y3, y4. Why is it that we are associating a probability distributions to them?
Why are we
associating a probability distributions to
Well,
them?
there's in the classification up here, there's only one distribution, P. It's just that what I tried to represent there was y1, so like the capital Y1, Y2, Y3, Y4, those are the labels, those are the classes that we're trying to decide. We're trying to decide which one of those to assign to this configuration X. And I just have wrote it 4 times because there's 4 classes and there's a probability associated with each one. That represents the whole of the distribution, right? So there's 4 classes. We need to have a distribution in this discrete space. We need to have 4 numbers that are non-negative that add to 1. And those represent, our estimation of how likely that thing is to happen.
So since y3 is larger, doesn't mean that.
Oh yeah, this is a problem. This is a problem with like probability notation. There's like a lot of the y. Yeah, so this is going to be mostly true throughout the semester. If a variable is capitalized in a probability setting, then it usually means it's a random variable. So it takes on various values, and the probability distribution tells you which ones it's likely to take on. And the lowercase ones represent like instances of that random variable. And I probably won't be very. I will try to be consistent, but I'm sure there will be times where I won't because it's sometimes annoying. And like a lot of times, capital letters will also be used to represent matrices, and lowercase letters will be used to represent vectors, which is still pretty consistent. But there will be some times where it will probably seem weird. And yeah, if it does seem weird, raise your hand and ask so we can clarify it. But all that means right there is that like this random variable y takes on 4 different values: y1, y2, y3, and y4. Yeah.
So if you want your outputs to be a probability distribution, what happens when you want to classify an image that might have 2 or 3 labels, right?
Yeah. So this is an interesting question about asking like what is the world, like what's in the world you're trying to model, and does it really have like multiple classes in it? So if it does, you actually want to learn that. So there's a variety of ways to go about that, but like just in the very simple framework that I put up here, this is a distribution, right? It's not like saying that it's definitely class 3. It's just saying it like mostly seems to be. And you might have a couple of those being, the same, and they're still like the largest ones, and you might use it that way. That's actually not the typical way to do it, but usually your labels will actually represent. You'll have there's actually a number of ways to do it that would take. I think we actually will touch on some of this a little bit later, but there's everything from actually learning multiple labels, like actually having multiple estimators or at least multiple outputs for doing that. And there are ways of actually letting the things that you're representing here actually represent more than just one class. So like a label actually represents multiple classes. And I don't know. And really, like, what's cool about neural networks is they're a lot like Legos. And I actually hesitate to say that because there's going to be a dumb Lego picture in a second. But they're a lot like Legos. Like you'll hopefully see by the end of this that there's basically like you can like put pieces together and get them to do all kinds of different things. And but they basically reside in some sort of framework that no matter what you build with your Legos, you can basically train it in the same way and hopefully get some learning. Other questions? Yeah.
So, in classification problems, are the neural networks explicitly calculating the y-hat for every possible network, like in the image processing ones? It sounds a little bit intractable after.
So I'm not sure what you're referring to. Let me just say this: the y-hat is a vector, right? It's just outputting a vector of numbers, one number for each class.
Mm-hmm. But I mean, like back to the image processing example that you mentioned, like it has to iterate through like man, guitar, cat, everything, all the possible corpus of nouns and assign a y-hat to that.
Well, so it's going to learn to do that on your training set. Your training set might be enormous. Your training set might be, millions of images. ImageNet has, like the full ImageNet has, which is like what a lot of stuff is trained on to do, the what's that called? The competition, like the classification competition, and it's got over 1 million images. I can't remember exactly how many right now. And yeah, like each one, like Coco doesn't have 1 million images. Coco has, I think it might be 60,000 annotated images, 40 something, I don't know. So it's not as many, but it's going to go through those. And it's going to go through those multiple times. It's from that data. That's like your one chance to learn whatever structure there is in it, and so you do need to go through it. That's why this is like super computationally intensive, and why you really couldn't make any good progress until you had GPUs, which is why you go through it really fast. Couple that with fast storage now, and you can do way more than you could do even a decade ago. I don't even know if that answered your question, but I probably didn't understand it right.
Okay.
Yeah. Okay. Yeah.
How do you determine how many hidden layers?
Yeah. So this is like the worst thing about neural networks, right? Is that there's so many configurations that could give you some sort of back off of the word configuration. There's so many architectures, ways of determining, how does this layer hook up to this layer? What's the size of it? And there's so many ways to do it, right? And it's not clear which one you should use. And there's really very, very little theory about to guide you in that. So basically, the way this works is you start with something that does well on a related task, and you start doing what's called hyperparameter searching, which is basically you keep trying new parameters, new architectures, and you see if that did well, and then you try another one, you see if that did well, and then you say, hey, this did well. And some people can actually do that, can actually have enough computational resources to do that, but most people don't, and so most people actually don't search it very well. So you sort of the space of networks you could use is enormous, and the space that you actually search is really tiny. So the question is how do I know if I've got a good one? This is a totally empirical science. It's terrible. This is that's why it's really terrible for a mathematician to be here, because it's so not math. It's the opposite of math. It's it's just experiments, There's very little theory. There's some cool theory, but it's very incomplete. Did that answer your question? Did it make you feel sad? Makes me feel
I
sad.
just want to add on to what she said. Can't we use a neural network to train? So, okay, not to train, but to modify another neural network that is already doing the task for us. Can't we do something like that?
Yeah, there actually exist papers that are, there's a paper called like differentiable architecture research or something like that. And it is using, there's like a meta cost function, and now I'm using language that we haven't really learned about yet, but there's like a meta cost function that's indicating, like allowing you to adjust the network in a way that should like be helpful, although it's really questionable, like if the cost function is actually knows about being helpful. Like this is the thing, like these kinds of parameters, it's hard to say, it's hard to write down something like that says, you know, if we're this different from each other, which way should I go to make it better? And this is like how neural networks work. They're all about like having some surface that you're walking on, and you keep going towards lower and lower places. So yes, there's some research on it. No, people don't really use it because it's just sort of questionable. But yeah, like you can feasibly think of these things. These are really awesome research areas that very smart people are working on.
Kind of piggybacking on that hidden layers question, but I'm kind of missing like how you're configuring weights as well in this like equation, like in the.
Yeah. So like the simple answer is I'm going to pick the weights that maximize the likelihood of my data. So like the probability that these points, all of these points in the data set are actually like in this data set. I'm picking the weights that do that. Now, there's no like simple algorithm for that, especially with these really complicated things. So what we resort to are techniques like gradient descent, which are basically we're going to set up a surface that describes where good solutions are, and it's going to live in many millions of dimensions, and we're going to try to like find a good local minimum of that surface. And there should be lots of questions about, is this a convex problem? No, it's not convex. It's actually super highly non-convex. Well, how do we know we get a good solution? We don't know. So like, why are we even doing this? Well, actually, it seems to work. That's really the answer. It seems to work. And there's all sorts of really cool research going on talking about like, when you do this like day to day, you see that this is really true. Like you can train the same architecture multiple times. You randomly initialize the weights in certain ways, and so you'll find different solutions every single time, like meeting local minima of this surface. And they're definitely different from each other, like in terms of like the actual values of the weights, and yet they give you equivalently good solutions. And this is seen all the time, and people are trying to figure this out. It seems like the current folk story around it is these things are in such high dimensions, like really like the standard ResNet 50, which is like a kind of a go-to convolutional network, has 25 million parameters in it. That's a really high dimensional surface to be like finding a minimum on. There's lots of local minima in there, and yet we seem to find the like equivalent one. So like, what's going on there? And it turns out there's like really cool connections to like statistical mechanic models, like spin glass models and things like that, if any physicists are out there, and showing that like because there's so high dimensions, there's tons of symmetry in the space, and this tons of symmetry turns into like equivalent minima all over. So I don't know. That's like there's not even a proof for that. That's just like, hey, like in this situation, you kind of observe that this is the case. So again, if you're one of the people who's actually enrolled in the math section of this, you really probably are sad right now, and I feel your pain. Yet, these work, and they work really well, and they're allowing us to do really amazing things. So you can continue working with toy models. I remember doing that was pretty fun. Or you can go to these models and not know all what's going on, but get the right solution. So yeah, it's this weird trade-off that like you have to make when you're thinking about what the type of science you're doing here.
As far as the prior, how good or bad is it to assume a normal distribution versus trying to actually find something about it beforehand?
Yeah, I mean, like, it just depends. Like, what happens usually is, and we'll go through some of these iterations, but what happens usually is like you pick a priority distribution like a normal distribution, and what will happen is that will translate into basically what's known as an L2 weight decay regularization. It just turns into something that basically is like penalizing large weights. You could put like a Laplacian distribution there. What it turns into is an L1 penalization. So it's both penalizing large weights and non-sparse weights. So like you can enforce sparsity. So like really more what these turn into is like there's becomes like this dictionary you look at it like, oh, I want sparse solutions that are, let's see, what's another common that you can put with that? I don't know. I want sparse solutions, so I put another one. Or I want really like a lot shorter solutions, so in magnitude, so I put on an L2. Or I might do a combination of both. Or, yeah, there's like tons of other things. So it's more like rules of thumb like that. Other questions? These are great questions. The kind of questions you should be asking at the beginning of a cool class like this. Okay, so I'm going to start into this in like the 15 minutes that we have. I probably won't finish it, but we'll finish it next time. And again, I have a schedule on Canvas. Having never taught a class like this, I really have no idea how long it will take to go through any of these topics. And maybe by the end, we've only gone through half of them. We'll make it to the end, and we've gone through all of them. I don't know. But I just warn you of that, and don't hold me to it. That I have to keep to that schedule because I probably won't. Okay, so first of all, I should say I have this next part. I've taken slides from the CS231N class because they're just like awesome slides, and I don't want to just like remake them. So I asked for permission, and I got transitive permission. I won't explain that, but I have transitive permission for using these. So the mathematicians are like, well, just woke up. Okay, so we're going to eventually be getting to convolutional networks, which are really great for doing a lot of image type tasks. Let's set up like the image classification task for a second. So the image part means we're using images as our data set. So typically, I don't know how many of you actually play with images, but typically what they are they're tensors. They have a certain number of pixels as their width, a certain number of pixels as their length or height, and then they have three channels. One encoding the intensity of the red signal, one encoding the intensity of the green signal, and then of the blue. And then those get combined together to give you this multicolored image. That's the kind of data we're dealing with. At every single one of these pixels, there are three numbers telling you the intensities of the red, green, and blue. And they're typically scaled between 0 and 255. That's the typical RGB image. Okay, so with data like that, we're trying to say things like, this will give you the simple world of like there's one thing that we care to classify here. We have a whole bunch of labels of what could possibly be in these images, and we want to pick out the right label. So like if this is a picture of a cat, we want to say it's a cat. And this actually was a really hard problem for a long time. It's actually like sort of trivially easy now, which is as long as you have good data. It's so weird how things change. So yeah, anyways, I guess I already said this, but there's numbers. So it looks like an image to us, but really there's just a bunch of numbers that are being turned into this nice visual representation. So there's a lot of challenges with this problem that make it hard. So one is, I might actually have taken a picture of this cat and at the same time taken a picture from a different point of view of this cat. Like from the back maybe, or from the side. And it's going to look very different, right? Like we're all pretty good at saying that's a cat, but it's going to look really different. And each of these points of view, we want to say that's a cat. There's tons of other challenges, like illumination. So like the intensities in these channels will change quite a bit depending on like the lighting in which the picture was taken. So these are all 4 different pictures, but I could take the same picture, like in bright light and a dark light, and it look very different. Like it's like the same thing in there, but it look very different. And we want to be we basically want to be like insensitive. Our classifier wants to be insensitive to those kinds of changes. I like this, right? Cats. I actually had a cat as a kid and then grew to hate cats. So there are no cats were harmed in the making of these slides. Somebody else made them. But I look at these and I'm just like, man, what an awful animal. But yeah, like cats in particular can get themselves in all kinds of crazy poses. And each one of these, we want to say that's a cat. We want to be insensitive to these like deformations in the object we care to classify. That one on the right is just like watching Netflix. Leave me alone, bro. Here's another challenge. We might not be seeing the whole cat, right? We might just be seeing a little bit of the cat. Thank goodness, just a little bit of the cat. Don't sit on that cat. There's like so many challenges, right? So sometimes like it's going to be really hard to distinguish the foreground from the background, or like the object that we care about from like its surroundings. So yeah, like this is a really hard problem. And this is why, like up until really powerful machine learning, like basically nothing happened in this field. I shouldn't say nothing, that's really unkind, but like very little happened. And then, lots of cats look different from each other. We all, in each case, we want to say that's a cat. So, in image classifier, here's our Python code, classify image, hashtag to do, some magic here, fix me, some magic here, return class label. This is like a really different kind of algorithm. This isn't like, this isn't something really deterministic in some sense, like I want to sort numbers or, I don't know, how much other algorithms you might think about. This is like really, there is some signal that is really hard to describe there that is a cat, and we want to figure it out. It's hard to imagine writing code that would be the ultimate cat classifier. Lots of people have tried to do this. This was like probably one of the most successful techniques applied to like lots of domains. You'd get these like contour kind of maps, and then you would like mark where all the corners are, and then you'd have these histograms of these corners, and then you'd say like, well, this histogram's kind of like this one, and that one was a cat, so this one's a cat. It sort of worked, but like only for a few labels, and really like it's laughable now. I don't have it in this presentation, but I'll make sure to put up another one where you can see the kind of progress that was made and how quickly it was made from 2012 on, when we had AlexNet, like the first really viable computational network. Like that's coming up in a couple of weeks. So, like, one thing that, and I have a link to something called Software 2.0 in Canvas, so you should go read that. It's a blog post by Andre Karpathy, which is really great. Like what we're doing, especially with neural networks, is we're basically learning to like write a new kind of software. Like this is not the hard-coded version of, here's a web page and here's where the picture's going to go. This is like, instead, what this thing is doing is saying, I don't know what the right thing is, but I know if I have a model that is flexible enough to learn to approximate a lot of different kinds of things, a lot of different kinds of probability distributions, and I have a good way of like adjusting to find within this algorithm to find the actual right network, then or model. It's not always a neural network, although it usually is. Then I have a chance of actually coming up with one. And again, I really won't know what's going on inside of this thing, but I just know it's a really great classifier. So, the way machine learning works really is to have these good networks or these good models that can really approximate a lot of different distributions and a whole lot of data that describes the relationship between, in this case, image and the class or the label. You have enough of that and a good high capacity model, you're going to learn how to do this. So yeah, so that's the name of the game. So just to sort of like motivate like how different this is from other kinds of machine learning that wasn't from that long ago, but seemed like a long time ago actually. Nearest neighbor. So nearest neighbor is like one of the simplest ideas in like trying to do classification. So you have a whole bunch of training labels, or training data, in this case images, and you have the correct labels for them. And basically, training just means I just keep a copy of those around. I just memorize them. I just keep a copy of all that stuff around. And then when I go to like say, what is this new image? Like, what's the right label for this new image? I basically look and say, of all the labeled data that I have and know about, find the one that's most similar. You pick some sort of measure of similarity. This could just be like, you know, these end up being vectors in a vector space. You just like pick some sort of vector norm to do distance, or a lot of times cosine similarity. So like measuring the angle between two vectors is a very common one. But you pick some sort of way of saying, what does it mean to be similar? And then using that measure, you go find the thing that's closest to it, and you say, and then you look at its label and you say, okay, this new example is from that class, and that's how you do the classification. So there's this great data set for doing a lot of toy stuff on. It's called CFAR10, and it just has 10 classes of things, and there are the 10 classes. Very common types of things. Airplanes, automobiles. Some things are kind of like similar to each other, some things are kind of very different from each other. But there's just a bunch of images. They're all 32 by 32, so 32 width, 32 height, and then RGB, so 3 channels. There's 50,000 training examples. There's 5,000 examples per class, so it's nice and balanced. There's the same number of examples per label. And there's testing images, so ones that you don't train on, but you use to test to see how well you're doing. And that's really important. I haven't actually talked about that as an important part of machine learning, but this is like very critical. You have to have some way of like talking about how well you expect your model to generalize outside of the training set. And there's all kinds of issues like overfitting that you want to protect against, and we'll kind of like touch on those things as we go, but it's not something I'm covering today. But yeah, so you train on the training set, and then you evaluate how you're doing on this test set. And yeah, this is kind of small, isn't it? So what this is showing over here is, here's some test images. So that first one up there is actually of a ship. It's kind of hard to see, but it's a ship. And what it's doing is picking one of those similarities, measures of similarity. It's asking what's the thing most similar to it, and then what's the next most similar, and then so forth. And it's hard to tell, but like in that first one, a bird came up for the first most similar, and then I think it's a cat, and then a deer, and heaven knows what that thing is, a frog or something, a horse. I mean, basically, there's not a ship until the 9th most similar one over there. The next one's a dog, and hey, look, there's actually a dog nearby it. But you can see like those two pictures are very similar to each other, right? Like you expect like under most measures of similarity to find this one in the test set, given this one in the training set. But then if you look at the next ones, like they're not dogs. There's a cat, there's a deer, and so forth. You can see that this isn't like doing very well, right? Yeah, so here's different ways of measuring, a distance between them. But here's how this thing works. Training just means I memorize, I just keep a copy of this stuff around, and predict. I basically just like loop over all the instances and say which one's the closest. And it's really terrible. It's really terrible. And it's terrible for a couple of reasons. So like one of the reasons is this. So an example is how fast are training and prediction. So I mean, training is just an order one operation. It's just like I just copy this stuff to memory and hold it there so I can work with it. But so like if I give it any size set of data, I mean obviously there are going to be some differences here, but basically it's constant time. But when I predict, I have to go through and compare similarity to every single sample in my training set. So however many there are, it takes some time proportional to the number of examples. And that's terrible, right? Actually, we want it to kind of be the other way around. We want training to be the slow thing, but prediction to be fast. We want to get our predictions as fast as possible. It's also terrible. Oh, do I not have that here? It's also terrible because, like, for images, like looking at the similarity of pixels, like it's like basically like you're like taking the same pixel from the two different images, and you're looking to see like how close they are to each other, and like that's supposed to be a measure of like how close these, like how similar in class space or in label space these things are to each other. And you can, as you think about that, you just know like that's terrible. That's not going to work, right? Because my cat could be like in the bottom right-hand corner, my cat could be in the top left-hand corner, and like those would not be found as being similar because like the cat things are in totally different sets of pixels. And I'll end with this. So what does this look like? So this is just like for multiple classes. You're just basically looking. You get these kind of funky boundaries for saying what's a certain class like. You don't have to just do one neighbor. You can do multiple neighbors. That sort of makes it better, but it's not all that great. We looked at this, but the point is, let's see. I swear I've got this here somewhere. Oh yeah. So the point is like this is terrible for images. This is really horrible for images for like various reasons. Because pixels just when you're trying to determine a class, the pixels are going to be in different places, and something like this can't work. And you have cursor dimensionality issues. So what we need is something different. So next time when we meet on Tuesday, we're going to talk about linear classification, which is one of the important building blocks of neural networks themselves. So again, homework, I will try my very, very, very best to get it up before the end of the weekend. Yeah. Oh, yeah.
We have to talk about a couple of things.
Yeah, Alessandro, sorry, some of you might need to run, I apologize, but Alessandro, our TA, wanted really quick to ask about hours, right?
Yes. So, okay, for office hours, I will be there either on Thursdays from 3 to 4, or on Fridays from 10 to 11 or 11 to 12, depending on your preferences. So, who wants them on Thursday? Please raise your hand. Fridays. And there's a lot of people that don't have preferences. It seems to me that Thursdays look